Hey class, welcome back. This is our next lecture on Unit 2. This time we're going to be talking about periodic trends. Our objective for today is to be able to classify elements and rank elements due to their trends, whether that's electronegativity, electron affinity, reactivity, whatever it is. Our goal is to be able to examine trends and rank elements accordingly. So today, in order to dive into what we're going to do, the first thing we need to understand is how do we look at the periodic table. Yes, we've talked about the periodic squares, but now we're going to talk about the table as its entirety. So the periodic table is made up of vertical and horizontal rows. Our vertical rows are our families, and our families share similar characteristics, while our horizontal rows are called our periods. So we have families going vertical, horizontal rows being periods. That's going to play a big deal. So whenever we start talking about these trends and we say, is the family decreases or is the family increases, or as we go from the lower period to a higher period, all that's going to play into effect with these. Or if we have a question that says rank these elements within this period, and we might throw an element that's not within a certain period. Okay, so keep all this in mind. This verbiage is important. So the first thing we're going to talk about is just kind of reviewing, but we're going to go through some of this, is protons. Protons, as we know, are positively charged subatomic particles. We know that the number of protons correlates with the atomic number. And so as we move across our periods, or as we move from left to right, the number of protons we notice increases. So does the atomic number, because they're the same thing. Also, as we go down the family, so as we go from the top of the family down to the bottom, the number of protons also increases. So we increase from left to right and from top to bottom. So that's your first trend, is the number of protons. It's a super easy trend. Then we're going to talk about our valence electrons and oxidation numbers. Remember, with our valence electrons, those are their outermost electrons. We want to have a valence shell that is stable. In order to do that, we need to have either 0, 4, or 8 valence electrons. That's the most stable forms of the valence electrons. Here are some things to keep in mind with this. Families. Same families have the same amount of valence electrons. So all the elements within the same vertical row or same vertical column are going to have the same number of valence electrons. Not the same number of total electrons, but valence electrons. Okay? As we move from left to right on the periodic table, we're also going to increase our number of valence electrons. So as we go from left to right, it increases. So if we move across our periods, they're going to increase, and as we move down our families, they're going to stay the same. They're going to be constant. Let's talk about this a little bit more, though. Let's go a little bit more in depth. Valence electrons and oxidation numbers. Okay, so oxidation numbers represent whether an atom has a tendency to lose or gain X amount of electrons. If it has a positive oxidation number, they have a tendency to give away electrons. So if I have a +1 oxidation number, that means I'm more likely to give away an electron than to take in an electron. And then if I have a negative oxidation number, it's just the opposite. I'm more likely to gain electrons opposed to give them away. So oxidation number shows the tendency whether to gain or lose electrons. If it's a positive oxidation number, or the element is willing to give away electrons. If it's a negative, it takes on electrons. So let's look at our periodic table. First, we're going to talk about the valence electrons available in each family. We're going to exclude our transition metals for now. That's for a later unit. So our first family, dealing with hydrogen, has a 1 valence electron. Okay, our second family, dealing with beryllium, has 2 valence electrons. Boron's family has 3. Carbon's family has 4 valence electrons. Nitrogen's family has 5. Oxygen has 6 valence electrons. It's anything underneath it has 6. Fluorine's family, or anything underneath fluorine's group, has 7 valence electrons, and anything in your noble gases or anything underneath helium has 8 valence electrons. Now let's talk about how that compares to oxidation numbers. Remember, these are whenever we add our plus and minuses to it. So, hydrogen's family has a +1 oxidation. Beryllium's family has a +2 oxidation. Boron's family has a +3. Carbon's family has a +4 oxidation. So anything underneath carbon has a +4 oxidation. Then we start going to the negative. So after carbon, we go to the negative. So nitrogen has a -3 oxidation. Oxygen has a -2 oxidation. And fluorine's family has a -1 oxidation. We can technically say helium's family has 0 oxidation number because they are very stable and they don't want to give up or lose electrons. But you'll never get problems saying, hey, this helium has an oxidation state of what? Okay, so what I would say is you go from hydrogen to carbon +1, 2, 3, 4. Then you go from nitrogen to fluorine, -3, -2, -1. So that's your oxidation and valence electron trends. So the next thing we're going to talk about is energy layers or energy levels. These correlate with your periods on your periodic table, so the horizontal rows. We're going to it starts up as a number 1 or 1 energy level with your hydrogen and helium period. Then our next period is going to have 2, and we're going to continue down until we get to 7, and that's your main chunk of your periodic table. From there, each horizontal row is considered an energy level. Now we get to that, we can start talking about shielding. So the shielding effect deals with protons in the nucleus and electrons outside the nucleus. We know protons are positively charged, and we know electrons are negatively charged. We also know that opposites do attract, like the positive and the negative are attracted to each other. Continuing with the shielding effect, electrons orient themselves in different shells. These shells are what we call our energy levels. So this is how we tie our energy levels into this. So the farther away the valence shell is from the protons, the more shielding there is going to be involved. So what do I mean whenever I say shielding? I mean, okay, we have our atoms, and we have our nucleus in the middle, and we have all these different layers. These different layers have electrons in them. The energy levels have electrons in them, and they are going to interfere between the protons in the middle and the electrons on the outermost valence layer. So the more layers there are in between, not only does it separate the valence layer by making it physically farther away from the nucleus, but also there's more electrons and different things in between the valence layer, the outermost layer, and your protons or nucleus. Since there's more stuff in between it, it makes the attractive forces between them weaker. When we're talking about shielding effects, we're talking about lessening the attractive forces between the valence shell electrons and the protons in the middle. So as we go down a family, so as we go down a vertical row, a family, our shielding is going to increase because we're increasing the energy levels. The more levels there are, the more interference there is between the center, the nucleus, and the valence or outermost electrons. As we move from left to right on your periodic table, though, your shielding is going to remain constant. So the big thing that affects shielding is the energy levels. If you go down the periodic table, you're getting more energy levels. That's going to increase your shielding. But if you move across the periodic table, that's not going to affect your shielding. Next thing, the atomic radius is the distance from the nucleus of an atom to its outermost electron level. So think of this like a radius of a circle. You take the middle of the circle and you go to the outer edge. This is the same concept. Okay? The number of opposing charges and shielding play a role in determining how big or small atomic radius is. So think about this. Okay, with our shielding, the more energy levels we had, the farther that outermost level was from the nucleus. So that would mean the number of, as the energy levels increase, that distance increases so is the atomic radius going to increase because you're making a bigger atom. So your trend for atomic radius is going to mirror the one for shielding. It's going to remain constant as you go across your periods, but as you go down your family, the atomic radius is going to increase. Why? Because you have higher energy levels. Okay, the more levels you add, the farther apart the atom spreads. Next is ionization energy. Ionization energy is the energy required to move the highest energy level electron from the valence shell. So basically this is saying, hey, ionization energy is how much energy is required to remove the electron that is the farthest away from the nucleus. Okay? Increasing bond strengths between subatomic particles make it harder to break these bonds. So, okay, we increase the energy or increase the bond strength. It's going to require more ionization energy to break that. So the energy between the bond strength between the nucleus and that outermost electron, the closer they are, the stronger that bond is, the more energy it's going to require to break it. Okay, that means it's going to have more ionization energy. Our ionization energy trend is it increases as we go from left to right on our periods, and then it increases as we go up our family, so from the bottom to the top. So ionization energy increases from left to right and from bottom to top. Then we get to electronegativity. So electronegativity is the measurement of the tendency of an atom to attract a bonding pair electron to it, or the likelihood of one element to take an electron from another element. So I like to think of this as the easiest trend to remember. You just have to remember one element, fluorine. Okay, the closer we get to fluorine, the more electronegative it is. Fluorine is the most electronegative element on the periodic table. So if we follow this trend, it's going to increase as we go from left to right on the periodic table or across the period, but it's also going to increase as we go from bottom to top on your families. So left to right increases, bottom to top. You're going to have more electronegativity as you go increase it. And our final trend that we're going to talk about today is electron affinity. So not electronegativity, but electron affinity. Okay, so this is the amount of energy released when an electron is added to a neutral atom to form an anion. So basically this is saying, hey, I have a neutral atom and I put an electron to it and form a negatively charged atom. Well, the energy that is released when that happens, that's the electron affinity. Your trend is going to be just like your electronegativity one. It's going to increase as we go from left to right, and also increase as we go from bottom to top. Okay? So just keep all these trends in mind. It might be beneficial to you just to write all these out. Definitions are going to be key when it is to understanding what's happening here. Outside of all that, we will have some practice problem videos to go with this, so don't be afraid to go look that up. And saying that, keep up the good work in the class, and see you next time.